Good morning, everyone. Can you hear me? Yes, very good. So I think we can just start. I have not prepared anything, as I warned you about. I have gotten a few questions on email, not too many. My general impression is that that many of you have gotten answers to a lot of your questions during the semester and on emails continuously. But hopefully some of you have saved some questions that you can bring to the table now. If not, then I'll start going through some of the questions that I've got on email. Maybe I'll just do that anyway, because some of them are relatively central, and I don't think that will take too much time. So I made a small note here, and I can share my screen. Not that one. Okay, so I made some notes here. One thing I've seen a lot of questions about, or just a bit of confusion about, is this concept of high resolution. What is high resolution? And the confusion is that when you are measuring resolution, for example, image resolution, we are giving it a number in millimeters or micrometers. And a high resolution means that this number should be as low as possible. So same thing with temporal resolution. A high temporal resolution is a low number for the resolution. So this is, of course, it's very confusing, and it's always been like this. But when I'm formulating myself, normally, for example, if I use this during an exam question or anything like that, then I will try to use terms like good resolution or improved resolution, so that it's not directly misleading, at least. So would be nice. I just want to clarify that, because that's always an issue. Okay, and another interesting question that I got is this difference between three things. One is beam width, then we have resolution, and finally extent of the PSF. And these three, they are sort of related, but they are not the same thing. For example, the beam width, that's the actual width of a beam, and a beam is either a transmitted beam or a received beam, and you can also talk about this abstract concept of a two-way received beam. But for example, for a transmit beam, then this would be the width of the actual transmitted field. So if you're sending a pulse with some focus depth and an aperture, then the resulting field will have a certain spatial region that it's covering, and that's called the beam, and that beam has a width. When you're in the image, then you are getting improved resolution, both because your transmit beam has some limited spatial region, and also because your receive beam has a limited spatial sensitivity. So you're gaining resolution both from the transmit and receive beam. So the resolution in the image will be affected by both transmit and receive beam width. And then finally, this PSF, this is the point spread function. And we can think of the point spread function as how far will the energy from a single scatter, a very, very small scatter, how far will that energy be dispersed in the image? How large region will that cover in the image? And the reason there's a difference between resolution and this extent of the PSF is that it's possible to have a small PSF, but if your imaging system uses a very low if it uses large pixels, or if you beamform with beams that are far apart, then you'll get poor resolution even though your PSF is very small. So it's not exactly the same, but they are definitely related. Okay. Then there's sometimes some confusion about gain, because this can mean two different things. But normally the gain that you've been using is image gain. This is the gain you apply during post-processing before you're making an image. You select the gain and the dynamic range. So it determines the intensity of each pixel in the image. But gain in ultrasound, specifically on an ultrasound machine, there's a knob that's called gain, and that might adjust not the image gain, but actually transmitted voltage. So you in some ultrasound systems you can reduce the transmitted voltage, for example, to avoid going in overrange, so saturating the ADC. So that's called transmit gain, or you can just talk about it as transmit voltage, and it's measured in dBs as well. Okay, two types of bandwidth. This has also been confusing for many of you, I think, because there are two main types of bandwidth that are important in this course. One is the one that's in fast time that we've been talking about the most. Everything before Doppler was then bandwidth was fast time bandwidth, and then referring to typically either the bandwidth of the transmitted pulse or the bandwidth of the received signal. Typically things that we looked at in exercise 3. The bandwidth in that dimension. So this is the signal which is sampled at very high sampling frequency by the ultrasound system after transmitting a pulse. That's fast time bandwidth. But after working with Doppler and PV Doppler and color flow, then we got another signal, the Doppler signal, which is sampled only at one spatial location over what we call slow time for different firings. So that signal, that has a sampling rate of corresponding to the Doppler PRF. And if you do the Fourier transform of that signal, then you typically get something that resembles the PV spectrum in some sense. And that spectrum has a bandwidth. So that's the slow time bandwidth. And that's also important in Doppler in general, because if your signal has a large or a high bandwidth, then it means that the spectrum is narrow, and it means that, for example, the autocorrelation method used in color flow will have more variance, because there's a larger frequency band, and this is a frequency-based estimator. So if you have a small bandwidth or a narrow band, then the autocorrelation estimator will be then it will be more accurate, and the PV Doppler spectrum will also be more narrow. Okay, so this is something that was related to exercise 3. We covered this concept of correlation length was more or less only addressed in exercise 3. So what's the relation between these? The pulse length. First of all of these are primarily referring to the axial or fast time direction. So the pulse length, if you increase the pulse length, so you get a longer pulse by using, for example, a higher number of cycles, then you will also increase your correlation length in the fast time direction. So that makes sense because the final received signal is a convolution chain, and one of the components in that chain is the actual pulse. So if you have a long pulse, then this will sort of cause correlation in this signal, because you're convolving with a long pulse. And then, of course, if you have a long correlation length, then this will degrade your your axial resolution. So axial resolution will be worse if your correlation length is longer. Okay, this is also a point which is related to lecture 3 and exercise 3, but it's also important in general during transducer design. So in exercise 3, we saw that because of this convolution chain, if you have a pulse which has a center frequency which is outside of the transducer band, then you'll do a convolution between two signals which have different frequencies, different frequency contents, and not necessarily overlapping. And when multiplying these in the Fourier domain, you just remove all the energy. So then you're left with very low signal and very low SNR. So to avoid that, you want your transmitted pulse to be within the transducer impulse response, in the frequency band of the transducer impulse response. That's important, and it's doubly important because your transducer is the one that's going to send your pulse into the medium. So then you get this impulse response on transmit, and it's also going to listen for the received signal when they are coming back. So if it's outside, then you get punished 2 times. So that's very central when you're designing a setup, that you make sure that you know what's the transducer bandwidth. Okay, sensitivity is a word that I'm using a lot, and maybe I've not properly defined what it is. But when we are talking about sensitivity, we are talking about our ability to sense or detect anything. So in ultrasound imaging, it means that we get a signal in practice. At least that's one interpretation of the word sensitivity that I'm using a lot when talking about ultrasound imaging. So if we have good sensitivity for some, for example, tissue structures or blood signal, then it means that the signal level is high, and in particular that the signal to noise ratio is high enough. So that's typically what I mean when I say sensitivity. Finally, a question about the Huygens principle and how this leads to the Rayleigh-Sommerfeld. What is the Huygens principle? So the Huygens principle just tells us that if we have a surface that's emitting an ultrasound wave, then a very good model of what is going on, we can get that by just inserting or modeling this surface as a series of very small collection of very small sources, where each source is emitting a spherical wave. So that's the Huygens principle, is that you can do this. You can model any surface as a collection of very many small sources. And if you then sum the contribution from all those sources, so you do an integral over the surface to calculate the field in the entire volume over time, then you get this Rayleigh-Sommerfeld integral. And we use this, and we from this Rayleigh-Sommerfeld integral, we went further and did some approximations, and that led to the Fresnel approximation and finally the Fraunhofer approximation, which is very central in this course. So the Fraunhofer essentially tells us that the field, either in the far field or in the focal depth, is proportional to the Fourier transform of the aperture function. So that's used as a guiding principle in a lot of ultrasound imaging. For example, when we apply apodization, then we implicitly use that the Fourier transform of the apodization window has lower side lobes than the rectangular function, which is the default. Okay, so that's questions that I got beforehand. So are there any other questions? feel free to either raise your hands or just pop a question in the chat. Okay, see now. So I'll put this in the notes. Okay, and then I can start thinking about what's going on. Why should the center frequency not be below transducer impulse and when the that's the PowerPoint, I guess. Okay, yeah. That SNR will be better the lower the center frequency is and the higher the number of cycles is. Okay, so maybe what I can do is, first of all, it's correct that in general, if you reduce the center frequency, then you will get less attenuation. Definitely, you'll get less attenuation, but there's more things influencing the final signal power. So if your transducer has a frequency band which looks something like this, and then if your default pulse center frequency is here, and then you decide that now you want to use another center frequency, let's move it even here, something. So you want to move to this center frequency. So then you will definitely get less attenuation of this new pulse with the new center frequency. But because your transducer has some has a different sensitivity for this frequency, then you might lose more than you gain. For example, if this difference here is let's say 10 dBs, writing here is kind of tricky, but I'll try. If this difference is 10 dBs, then first your pulse will be 10 dB weaker. Your transmitted pulse will be 10 dB weaker, and then when this signal is coming back to the transducer, then your transducer will also receive this signal as 10 dB weaker because of the sensitivity function of the transducer impulse response. So all in all, you lose 20 dB. So you need to evaluate if your attenuation at this depth you want to measure is that would that be altered by more than 20 dB? Then it's okay. Otherwise, it's not worthwhile changing the frequency. Of course, if you start off here, this is your default pulse at this frequency. But if you now decide to go down, then you get double the gain. So you get more output of the transducer, better sensitivity on receive, and you get less attenuation as well. So then you get a lot more signal potentially, but your resolution will be a bit worse. So that's the trade-off typically. But at least take account also both the transducer impulse response and attenuation. And that's you need to account for both. Yeah, so the peak is typically the peak is what they give as the center frequency, but that's not an absolute. But that's ideally the transducer impulse response looks like a perfect Gaussian. But in practice, I've seen transducer impulse responses going something like this. That's not uncommon at all. So then maybe they are saying that the transducer center frequency is here, but you have a large band here that you can use potentially. But if you're working with ultrasound design, then you actually get access to to some transducer impulse responses. It's part of your input when deciding on setting up an acquisition sequence. So then you get the actual frequency response of the probe. It's also possible to measure this. You can go in a water tank and then you put an hydrophone below the transducer and you measure the pulse. You do a Fourier transform. So you just try to make a very short pulse, as short as possible, and then you do the Fourier transform. Then you can measure the impulse response of the transducer. Okay. Okay, so I'll also put that. If expanding aperture is regarded to be a form of dynamic focusing, I would say that they are not the same thing, and they are separate, but they are often used. They are used together in a sense, but dynamic focusing is just that we are focusing at all pixels in the image during reception. So when you were doing beamforming in exercise 6, those of you who did that, then you got the channel data and you applied delays, and you needed to select different delays for each individual pixels. So then this process of using individual delays for each pixel, that's called dynamic focusing. So that's possible to do on receive. Expanding aperture, on the other hand, that's specifically this thing we are doing when we are using a different number of channels during beamforming, depending on the depth of the pixel that we are beamforming. So if we are if I clear the board here, let's see now, clear. So if we are beamforming this point, then we are maybe using this aperture here, and then we have more elements available on the sides here that we are not using. But when we are summing our signal, we are using these channels. But if you're beamforming a point which is deeper, then you decide to use more channels when you're summing in the summation when doing receive beamforming. So then these two will have the same receive F number, the same angle here. This half angle here determines effectively the receive F number. So they should be the same. So as far as possible. So that's expanding aperture. So it's not exactly the same as dynamic focusing. Dynamic focusing is always used in a modern ultrasound scanner, or not always. If it uses software beamforming, then we use dynamic focusing. So maybe in some analog setups, then you don't. But it's definitely you gain a lot by doing this. Okay, exam questions. Exam 2023C. Okay, so there's a question regarding that. I can bring up the exam. So the question is, yeah, okay. This is a very central kind of question. So what we want to do, yeah, it's B mode, and we have an imaging system. We have typically gotten some parameters like firing rate and center frequency, number of pulse cycles, and we want to determine the spatial resolution. So, okay, that's a very typical thing to do. And so it's sort of one of the very fundamental things in the course. So let's see now if I have text. So spectral resolution. It's always I use normally the -6 dB like approximation, But this factor of 1.2, it's I say that
we don't see your screen if you're writing something.
Okay, I thought I was sharing my Blackboard. Can you see the whiteboard now? Maybe I can just share my screen and then bring up the whiteboard. So let's see. Do you see text on the whiteboard now?
No.
Okay, sure. Let's share screen then. That was a bit weird. That's probably a technical problem. So what happens if I do this and this? Test again. Seeing text on whiteboard now?
No.
Okay, just a minute. So that's probably a Blackboard bug. So now I stop screen sharing and then I do this. Seeing the whiteboard now?
No.
Okay, what's going on? Oh, maybe, okay. Oh, let's see, okay. So now I've written lateral resolution. Okay, very good. Okay, then I'll proceed. So then I'll bring up some text. So, or we can do it in another way. Since it's just text, I can share my screen, and then I can do it in Word, so it's more interactive. Okay, so lateral resolution here, like this. Okay, so I normally use this approximation, so it's minus 6 dB. But this factor of 1.2, if you omit that and then use just f number lambda, then it's perfectly okay. So that's the beam width normally. But if you want your image resolution, then you need to have this f number to be two-way. And the two-way f number is f number two-way. That's this formula, which is 1 over the f number on transmit, 1 over the f number on receive, and then this always should be inverse. So that's the two-way f number. Remember, once I'm talking about the image or image resolution, then use the two-way f number. So if I'm talking about transmitted beam width, then you use the one-way f number. That's a very common thing to miss, definitely. So I need the two-way f number. So I have that here. Then the lateral resolution is given by this. And here we have lambda. So I have probably here. Lambda is the most commonly used symbol. Okay. That's the lateral resolution. I'm not sure if I'll bother to insert all the numbers if I just want the general. So, and lambda is of course c divided by center frequency. And then the axial resolution is the pulse length divided by 2. And that's typically equal to lambda times the number of cycles divided by 2. Okay, so then I'll just clarify one thing about lateral resolution, because that was part of the question. So this is an approximation that's following from this k-space analysis of the point spread function. So then we derived that this two-way f number has this form. But if you know that you have the same aperture on transmit and receive, then you can improve this estimate somehow. Then we know that the sinc function, sinc squared, has minus 6 dB beam width, which is equal to 0.88 f number times lambda. And that's and then this is now the one way. So TX or RX, they are the same because you're using the same aperture on transmit and receive. So this you can verify if you plot the sync squared in MATLAB, and then just measure the -6 dB. You take the 20 log 10 of that function, and you measure the -6 dB beam width. You'll get 0.88 and times f number lambda. This isn't a specification, or it's another approximation. So I know that some students know this and then they just use this, and that's okay. And some students just use this two-way f number, and that's perfectly okay, even with or without this 1.2 factor. And then a lot of students then just use the one-way f number, and that's not okay. Then you get point deductions. Okay, and then elevation resolution finally. Then it's still 1.2 f number lambda, but now remember that f number should be elevation. And elevation f number, then you need to calculate this as so f number on elevation. That's the depth divided by elevation aperture. So it's the size of the aperture in the elevation direction. So, okay. When you have rectangular aperture, if you have rectangular aperture and you're using the same aperture size on transmit and receive, then you get this this formula. If you're using the rectangular aperture and you have different sizes, then you can use this. If you're using a Hamming window or a window function, apodization function, then I guess we still use this, but then it becomes an approximation. Then we know that this is just an approximation, and in some sense it's just an approximation regardless. So, but we just know that this is the main approximation for the resolution. And if you use a window function in addition, then we know that main lobe will be wider and you get reduced side lobes. So, but we have not tried to quantify that. Of course, you can simulate it or just do numerical calculations. You can do that, but we've not done that. Okay, so definitely calculating resolutions. I think I've given that as. I think that's always been part of the exam, without exception. So you should be able to calculate image resolution somehow. Okay, so inclination and critical angle, how it affects PSF and ultrasound image. Okay, so then I think I'll go back to the whiteboard. So now I can try drawing again. Let me know if you don't see things. So the thing is, when we are imaging, we have a transducer here now on the right. And then we have an active aperture. Let's say that we are using an aperture which is here on the sides. So we use this part of the aperture here. And then we are imaging a point which is here. This is just to illustrate. So then we now, these elements, they are transmitting and receiving signals which are sort of spanning this sector here. So any pulse is propagating from here and then down to this scatterer, which is here. And then the backscattered echo from this scatterer is coming back to the transducer. And for example, this element here, that will see a signal which has been going in this direction. And what happens then in K-space is that because the oscillations seen by this element when transformed to the image will be in this direction, then in K-space it will be along this in this region here, along this direction here. So that's the energy seen by that element will be along this direction, same angle as here. So this angle there will then be the same as this angle here. That's so this element is contributing energy in this direction, and then the pulse will also have a center frequency and a bandwidth, and that center frequency can be converted to spatial frequency. So that's here, let's say, and then it has some bandwidth here. And then if you look in K-space for all the different elements here, then you'll get this band here, which goes along this sector going here. And this stops typically, let's say here. For this case, now we stop here, and then you get this part of K-space. So then we have our energy is confined to this region. And how does this affect resolution? It very directly affects resolution. So now that we've done the calculations or the just observations on where is this energy in K-space, then if I want to say anything about resolution, I would do something like this. I take first the axial direction. How large is this frequency content in the axial direction here? And if I then take just this is some spatial frequency, and then the resolution is typically something like the inverse of this. So if this is some k set, and then f k set, then the resolution, if I can call that delta set, will typically go as 1 over this fk set. So there's a direct inverse relation. Similarly here, so here you'll get this fk set, now kx, sorry, fkx, and then this resolution is something like that. Okay, so that's a very direct relation, inverse relation between this extent of this point spread function in K-space and the resolution in true space. And then, of course, remember we talked about this earlier, that this explains it gives us the extent of the point spread function. But then in the final image, if you undersample it either axially or laterally, then you will get worse resolution. But this is the limitation caused by the PSF. Okay, so then there was a question on the exam, similar form and difficulty level. Before you have taken the exam, I can't say for sure, but it's not going to be something radically new. I think it's along the same lines. So also last year the exam was digital and with all aids permitted. So I would say that it's along the same lines as last year. Okay, lower PRF when interleaving. Why do we want that? So just save some questions for later. Okay, so I'll try to clarify about interleaving and PRF and what's going on there. I'll try to do that. I think the whiteboard is an okay place to work with this question as well. So normally when doing interleaving, and maybe I can use the slides instead. I think that's so. Let's see if I have okay. Okay, so interleaving. What is interleaving? So interleaving is that we fire first a set of fires in different directions. So the consecutive firings are going in different directions, but then at some point we go back to the first direction, and we do this multiple times, covering part of the image and then moving on to the next interleave group. So covering the next part of the image. So the alternative to doing, there are two alternatives to doing interleaving, and one would be to fire all the firings we need in one direction first. So this would give us a higher Doppler PRF. So we would be able to measure higher velocities. But the total observation time of the scatters of the signal that we're interested in is lower. So that's the trade-off. If we use interleaving, then we reduce the Doppler PRF, and this is not necessarily an advantage. That's not the goal in itself. But the advantage of using interleaving is that we are getting a larger temporal observation window, a longer temporal observation window. So when we can observe the scatters for a longer time, then we get better clutter filters typically, and we get better velocity resolution. In general, we are much better at measuring lower velocities. So if you're interested in low velocities, then you're definitely motivated to use interleaving. If you're interested in measuring very high velocities, then I would recommend doing something like this. So lower PRF is not, lower Doppler PRF is not an advantage in itself. The advantage of using interleaving is a longer observation window. Okay, anything else that's unclear, difficult topics, anything like that? Yeah, sure. For me, a 15-minute break is perfectly fine. Okay. Okay, sure. We can take a 15-minute break, and then I can go through all your questions afterwards. That's a nice way of doing it. So I'll start answering questions again at 7 minutes past 11. Okay, then it's 7 minutes past 11. So continue answering questions. So I just want to comment on this critical angle that we discussed, because it's said here that the critical angle is arctangent of 1 over 2 times the f number. And I guess if you have the 2a f number there, then it's not correct. I'll clarify. So in K-space, we have gone through 2 different. We did the calculations first for the one-way beam. Then you have this critical angle here, and this is the, I'll try to write this, arctangent, oops, like this, of 1 over 2 times the f number. And this is the one-way f number. So for example, in transmit, this would be the transmit f number. Sorry about the handwriting. But if you're in the two-way, scenario, then the correct expression should be I can do something like this, I think. Whoa. Okay, sorry about that. Okay, I'll just write it here. Then the correct expression is arctangent of 1 over 4 times the 2a f number. So I think, so it's like this. So I think I'll move to the document instead, where you can actually write. So then for the 2a case, then it's of 1 divided by 4 times f number transmit receive. And if you are using now the same aperture on transmit and receive, then we know that this is equal to half, so same aperture px and rx. Then we get this, and then this expression here, then this simplifies to 1 over 2 times the f number, like this. So then it's the same angle. So if you're using the same aperture on transmit and receive, then the critical angle is the same as the one-way case. But if you're not, then it's not exactly the same, because you're using a different aperture on receive. So then the correct expression is actually this. It's 1 over 4 times the 2a f number. So this expression is always correct. That's always correct. This is correct for the one-way case, and you can use it if you have the same aperture on transmit and receive. And rectangular representation, I guess. Okay. Then there was some exam questions. So now we're going all the way back to 2014. So it was here. So I'll just already state here that this is strictly spoken. It's covered by the curriculum, but the focus of the course has moved a bit away from the details of this spatial impulse response and describing that. Although from what we have learned, it's perfectly possible to do this. But I'll draw. So the scenario was that you have a focused aperture looking something like this, and then you have a spatial point here, and you're focusing towards this point, and it's now focused. The beam is focused, so if it's focused in this point, then the signal arriving. So if I draw the received signal here down on this axis, then it will be 0, and then once you get to the correct depth, then you will get a very clear spike in energy, and then so that's the impulse response of a focus beam as measured in this point. So the transmit spatial impulse response. Now, if we move this point to a different position, so that we are now on the edge of the aperture, so we're still focusing in this point. What happens now is that the first echo arriving will be from this element here on the side. The first echo arriving will be from this element here, and that echo will turn up at the same depth, like this. But then, after this echo has arrived, then you'll get a series of echoes from the entire aperture, from all the elements along the aperture until we get to the end. So then you'll get sort of a series of signals. So, and that will end when you get the signal from the leftmost element here. So you start getting a signal when you get the signal corresponding to the propagation time on this line going straight down, and then it ends when corresponding to the time to this propagation length here from the leftmost element to this point. So then you get this impulse response. And then I guess the question is, what happens if you now send a pulse, not an impulse? And then in the first case, you just get the convolution between this impulse response function and the pulse. So then you'll get the pulse, which is sort of centered at this position. So poor pulse, but regardless. In this case, in the case of being on the side, so the red case, then if you do a convolution between the pulse and the impulse response function, then first you'll get the contribution when you get the first boundary, like this. And then during the constant phase here, then actually the pulse, it will be added to itself. And because the pulse is balanced, it has 0 energy for the 0 frequency, then you get no signal during this period. And then finally, when you get to the lower edge, then you get the inverted. So it's when we're hitting the boundary, you sort of get the derivative of the pulse here and here. So it's just a convolution between the actual pulse and the impulse response function. So similar to what we did in exercise 3. So then there was also a question on task 2F, but I think I'll skip that because the task in 2F was to calculate axial resolution, lateral resolution, and then elevation resolution. So it's essentially the same thing as I've already gone through. Again, remember that to calculate elevation resolution, you need to use the F number in elevation. So you need to know the size of the aperture in the elevation direction. Okay. So that's it for those questions. So far, no other questions turned up during the break. Do you have anything now? Okay. Why we need to downmix after doing the Hilbert transform? Okay, that's a good question. So I'll do the Hilbert question first. And the answer is sometimes you don't. You don't need to downmix. For example, if you're doing the signal after Hilbert transform, it looks like this. It's just a high frequency signal, and then you can downmix it to the baseband or not. If you're doing normal B mode imaging, if everything you're going to do is just to find the envelope, then you can just do the Hilbert transform, take the envelope, and then you are done. It's perfectly okay. If you want to do any sort of interpolation on the signal after beamforming, actually in the beamforming process also, let's say that you're downmixing or demodulating first, and then you're beamforming afterwards. Well, when you're doing beamforming, then you're actually summing channel data. So the channel data grid you have here. So this is fast time is down here. Fast time is here, and then channel data is here along this axis. So then you have some delays that you want to sum. Delay profile. When you sum this delay profile, you actually do interpolation of the data. Thing is that if you do interpolation of data that has high frequency content, then you get an implicit interpolation error because of the high frequencies. Interpolation often works as a low pass filter, so you get some you lose some energy in the high frequencies. If you demodulate first or downmix first, then it's all low frequency. So then interpolation during beamforming is more correct. So that's an objective advantage of actually downmixing. So interpolation, yes. So when we do summation, for example, when we're doing beamforming, then we have a grid of data which is in a 2D matrix. So I'll just illustrate that here, like this, very simplified. So there's many channels and there's many depths, but then you have a time of flight curve that you want to interpolate, and that goes through your sample data somehow, like this. And then before you sum, what you actually do is you interpolate the data at specific points. Here, 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 and here. You need to evaluate your channel data at those points, and those are not exactly on the grid points. They're not on the sampling points here. So that means that you need to do interpolation. And if those data are high frequency, then you'll get more interpolation error. That means if it's close to the Nyquist frequency, if it's closer to the Nyquist frequency, you get more errors. So objectively, you gain something from the downmixing. In Doppler, actually, there also you don't really need to downmix. The main advantage is anything you do numerically, interpolation, all these things are much better behaved when you're working on low frequency signals. Okay, so 2C in 2017. So let's see what that is. Okay, time of flight. Yeah, okay. So it's relevant for this discussion on beamforming. So this is just calculating the time of flight, but given a transmit and receive point location x set. The difference between this scenario and the one that maybe was on the slide of some lecture 5 or 6, is that in this case, the transmit beam is also focused at some point, which is not straight down. So then then what happens is that your transducer is here, and you have a focal point here, and it's not straight down in a sense. So you are sending a focused wave towards this point here. And then we are now modeling this. The transmitted pulse is always modeled, or the transmitted field is modeled as a wave front that's propagating through space. So in this case, it's a focused wave. So it will look something like this. The wave fronts, they look like this, focused wave. And time 0 is when this wave is passing the aperture, and more specifically, when this wave front is passing the center of the aperture here. So, like this. So this is the center of the active aperture. That's the definition of time equal to 0 in beamforming and time of flight, when the wavefront is passing through the center of the active aperture. And then the propagation direction of this focused beam is along these, perpendicular to these wavefronts. So it's directly from the center of the aperture until this point. So then the contribution to time of flight here. So this is the propagation distance on let's call it d, the propagation distance on transmit. Now this becomes not just the depth; it's now the square root of this is x set. Do my best here, and this position here is now let's call this e x 0. Okay, so then this becomes x minus ex, like this, squared plus the depth squared. So the transducer is still at 0 depth, so the distance is. Okay, so that's the difference between this and the other time of flight, which is on the lecture slides. So, but the general principle is the same. The case in the lecture is a special case of not using steering. So when you're not using steering, then the point is on the center line below your active aperture. So then the propagation direction is straight down, and then this term with the x's that will disappear. Then it's just the depth on during transmission. So in general, you need to take care if you're steering. When you are calculating the time of flight delay, what you do is that you assume that t equal to 0 is the center of the aperture, and that's a convention. So it's not an absolute must, but you need to use that convention both when you're calculating your time of flight delays, your time of flight, and when you're putting a time axis on your channel data. So when you have your 2D matrix of channel data, then you need to calculate the times along the fast time direction. So then you use this convention. Time equal to 0 should be when the transmission is passing the center of the aperture. And then you calculate the time of flight with the same convention, and then if you do both, then your beamforming is correct. Then you get focusing. Yes. So I think that covers the beamforming question. Okay, let's see now. I think I'll do the last question first. So that is to explain what happens in the frequency domain. What's meant by linearly varying phase? Okay. Yes. Yeah, this is this should be explained. So first of all, you have a time domain signal and you multiply it by a real valued amplitude signal. So let's see now. We have a time domain signal like this, and then you do have FFT space here, Fourier space, where this is a bandpass signal somehow. And then, so maybe even easier if we let the signal be a very long sinusoid. Very long sinusoid, and then it's very narrow band in Fourier space. And then you multiply this first by an envelope function. What happens then is a convolution in Fourier space. So then you actually get the Fourier transform of this envelope function convolved with this. So you get this. And then the other part is if you multiply it with the signal with constant amplitude but linearly varying phase. So that means that you're multiplying this signal here. You should multiply that by a function which has constant amplitude but linearly varying phase, and that typically looks something like this. So this is a signal. So this S is your original signal, and this is your signal that has constant amplitude but linearly varying phase. So what happens then in the Fourier domain is that this frequency here, it experiences a frequency shift. So it's for example, the thing we're using when we're down mixing. So then this frequency shift here, this delta F, that should correspond to this omega here. So omega is 2 pi f. So this should be omega divided by 2 pi. Okay, so that's the signal with linearly varying phase. That's a signal which is used for example, for down mixing. It's also the kernel in Fourier transform. In Fourier transform, you use this signal as the kernel in the integral. Okay, 2019 3b. Okay. I need to look at that. We were here. This is question 3b. So here we see two spectra, and relative to the Nyquist velocity, then these have the same. If you had taken a line and drawn a line through the center of this frequency band, then that line would be the same for both cases, relative to the Nyquist velocity. But we also observed that the velocity axis changed between these two. So then what happened is that you have you're depicting the same flow, but you're using a different beam to flow angle. So you have tilted your probe somehow so that the blood flow is now going in a direction which is different from the original one. And what we see here is two things happening at once. When you change the beam to flow angle, then the Doppler shift, if the beam to flow angle becomes closer to 90 degrees, the Doppler shift, it decreases. The Doppler shift decreases, it goes towards 0. but the Doppler signal has the same bandwidth, or approximately the same bandwidth, because the scatter is still moving with the same velocity. So it uses the same time through the sample volume. The transit time is the same. So overall, the Doppler shift is lower. So the Doppler shift frequency is lower, but it has the same bandwidth. That means that the relative bandwidth becomes higher. So then after angle correction, you see then that the relative bandwidth of this signal is much higher. And that's what happens when you increase the beam to flow angle. Okay. How you get the equation that the true velocity? Yeah. Okay. Yeah, this is a central question as well, regarding this conversion between the true angle and the axial component of the velocity. So you have an aperture here, and then you have a scatter here, which is now moving in some direction. Let's say it's moving like this. Something like this, yes. And then you're, let's say you're steering the beam in this direction here. That's your beam direction. So now this scatter, which is moving in this direction, the absolute velocity is given by the blue arrow. The velocity which corresponds to the shift we are measuring, there should be 90 degrees here. That's here. So that's the red arrow here. And then the beam to flow angle, that's this angle here, theta. Let's say it's called theta. Okay, so then now we get that V. Let's see now. So the 90 degrees is there. So we have V true. So this angle here has, this is the hypotenuse, and this is the, so it's the cosine of this angle is the red divided by the blue. So come again, the cosine of theta that should be the V axial. Sorry about the messy notation. So it should be the axial velocity divided by the true one. So then we get that the axial velocity is equal to the true velocity times the cosine of theta. And the Nyquist limit, is a limit on the axial velocity. So it's the Doppler shift you're measuring, or the phase shift you're measuring, is corresponding to the red velocity component there. So you can have very high velocities in like the blue arrow can be really long, but if this component is below the Nyquist frequency, then at least your center frequency is not aliased. But when you get high velocities, then you get a higher bandwidth. So that you get a higher slope. So that can cause problems. But at least the aliasing limit is a limit on the axial velocity. Okay, yeah, and then I sort of partially answer the next question. So the question is, if we can increase the beam to flow angle, then you can measure higher velocities without aliasing. And that's, to some extent, it's true. But this benefit is cancelled by spectral broadening, and it's even more cancelled by the fact that you're not able to estimate the angle very well. So if you turn this equation on, you see that the true velocity is this axial velocity divided by the cosine. And if, let's say, your beam to flow angle is 80 degrees, in an extreme case, cosine to 80 degrees, that's 0.17. So the conversion factor there is 5.7. If it's 85 degrees, then the conversion factor is 11. So it means that if you're by 5 degrees, then you get an error of a factor of 2 in error. And that's a very critical regime to be in. No clinician is able to determine the beam to flow angle within 1 or 2 degrees consistently. At least I wouldn't bet any diagnosis on that accuracy. So in general, a guideline for clinicians is that angle correction should be on beam to flow angles that are less than 60 degrees. 60 degrees. But with that said, then when doing vascular imaging, then often they image with the beam to flow angle of 60 degrees, and they do PD Doppler and they do velocity estimation. And it's not perfect; they still do mistakes, but at least the consequences are not as critical as if they had used higher beam to flow angles. Okay. I can give you just a few pointers on the exams based on previous years. I would say that if when working with the exam, if you encounter a problem which you think is difficult, then take the easier problems first. So that's sort of a given, but it's easy to forget and think that you need to do all the problems in order. So it might be a tip to do all the problems that you're able to do first, and then do the trickiest problems last. And another thing is, even if you encounter a problem which you're not able to solve fully, you can probably still get a lot of partial credit by answering or just writing something which is relevant for solving the problem. So often I've seen many good students leaving problems unanswered, where they could have gotten probably a lot of points by just stating things they know that could be useful for solving it. So that's definitely something to remember. If you write nothing, then it's very tricky to argue that you should get points. Okay. Any other questions? Okay. Back to 2014. Okay. Yeah. So this is the same problem as earlier, and the D here is, I think the focal depth was the geometry here. I think the focal depth here in this case was 20 millimeters. 20 millimeters, let's say 20 millimeters. So that was the focal depth. The original focus is here. The focus is in the middle, but now we're on a point which is on the side. And then the aperture size was 10 millimeters, I believe. So this was this is the focal point, and then it moved 5 millimeters to the side. So half the aperture is here, 5 millimeters, but the entire aperture is 10 millimeters. 10 millimeters here. So then the first echo, that's coming from this element which is here, straight above this point. So then this has traveled for propagation depth of 20 millimeters. But the last echo has traveled from this point here to this point, and then this distance here is the square root of 10 squared plus 20 squared. So that's why the d is this distance. Okay. Any further questions? We still have some time. Okay. Yeah. No, there will be, everything will be in like digital text fields. So if you're writing equations, first of all, any exam in this course, at least the later years, you're not going to experience very long calculations. That I'm not, you shouldn't expect that. So it'll be more about concepts, and you should know, of course, to the fundamental calculations. There will be some of those, definitely, but not very long derivations and with many expressions. So the way to write those, I think there's also an example on given with exam. So when you're writing expressions, then you can just write them in one line. So what's the Nyquist frequency? It's C times PRF, and then once you, if you have fractions, then use parentheses so that there's no ambiguity. So something like that. So you won't get those very long derivations. So I don't see the need for scanning in anything by hand, and it's also more convenient for you. You don't need to think about those logistics. So last year, at least, that was not a problem. So I think it should be okay. Mm-hmm. Okay, going all the way back to 2012 now. See what we got there. So the older the exams are, the further your sort of the focus of the course has changed gradually over time. So, but of course, some of the problems are definitely relevant. So now this was 2C. Okay, so this is a calculation of point spread function. Okay, so actually here the approximation is used as the lowest F number of transmit and receive. I would say that that's not accurate. That's an approximation maybe, but I would say that you should use the expression for the two-way F number, and that's a much better approximation than just using the lowest one. So of course, using the lowest one is an approximation, because that corresponds to the narrowest beam. So your transmit beam is wide, and then you have a receive beam which is inside the transmit beam. So it's reasonable to say that the resolution is approximately corresponding to the receive beam, because it's the smallest one. But you still get some weighting from the transmit beam. It matters to some extent if the transmit beam is large or if it's wide or almost as narrow. So use the expression for the 2AF number, and then you get an answer which is more correct. Yes, so keep it simple. Anything else? Okay. Now, all the way back to 2010, do we even have that exam? Yes, we have the exam, but not the solution. Okay, very good. So 3D. Okay, let's see what we have there now. 3D. Oh, okay. That's an interesting question. Is it possible to calculate signal power, mean frequency, or bandwidth from just the real part of the Doppler signal samples? Okay, so I'm not. I need to think about this question a bit. So, first of all, if you only have the real part of the Doppler signal, the Doppler signal is complex. So you have thrown away. You have thrown away a lot of information if you just use the real part. So my immediate answer to that is that you could definitely estimate signal power. You could definitely estimate signal power because on average, the real and imaginary part, they are expected to have the same power. So you can estimate the signal power, but anything else than that might become tricky. Especially the mean frequency, I don't think you'll be able to retrieve that. But I'm not 100% sure, actually. Maybe if I get a more confident answer on that, I'll post it. But my very clear guess, almost 100% sure, is that you can estimate signal power, but not the other two. Yeah, so you can't find the conjugate. No, you can't find the imaginary part if you're only left with the real part. So in general, if you have the IQ signal, so you have demodulated and then this, if you remodulate so that you get a pre-envelope and then you take the real value, then you actually regain the RF signal. So then you're actually okay. Then you have all the information there still. But if you have the demodulated signal and then you take the real value, then I can actually show this since we have time. So if you have the pre-envelope signal, so now you have demodulated, you have the IQ signal, but then you actually remodulate it so that you get this, and then you take the real part, then you get the signal here with the copy here back. So then you get the RF signal back. But if you have the IQ signal and then you take the real part of this, then what you do is that you will now put this component here on top, and you get this messy signal, which is now symmetric. It's real valued, but you've destroyed the frequency content to a certain extent. So I would not be starting calculating mean frequencies from that signal. So it's not well defined. But if you had remodulated first, upmixed the signal first, and then taking the real value, then you have all the information there. So then you can do things. Okay. Which exams or years are the most relevant? They become more and more relevant the more recent they are. So the course has evolved gradually over the years, and I would say that the last exams are definitely most relevant. Oh, and especially last year's exam was also digital. So then you had the same aids available during the exam. So the questions, they are in the same type as the other years, but because you have all the aids available, then we can't just give you questions that you can copy paste from slides and so on. Then we wouldn't be able to distinguish between students. So there's definitely some questions you can probably answer by copy pasting from material that you have, but you also need to show understanding if you want the best grades. Okay. I would say that I don't think you will get extended times for potential scans, because the exam is not expecting any scans. So all the answers should be in fields, digital text boxes. So as I said, I don't think you should expect any long calculations. They should not be necessary. So of course that also limits how much I can't expect you to draw or sketch things that much as I could do on a normal exam. So that you should also know that. Okay, it feels that we are nearing the end. I'm still impressed that you were able to fill 2 hours of content with questions. Okay, so if there are no further questions, then all that's left is to say thank you for this year and good luck with whatever you're doing in the future. Some of you have been in contact with people from the ultrasound group and me regarding projects, assignments. Okay, so now we got the question, so I'll take that as well. Yes, I can repeat that. That's an important distinction. So we can have a PSF. We can have a PSF that looks like this, maybe some side lobes like this. That might be an extent of an PSF defined by the size of this blob here. So that's the extent of the PSF. But in the image, then you will have scan lines. So when you're beamforming, you are making image lines. So maybe when you're imaging this, maybe in one case, then maybe your imaging lines are densely sampled so that you get you can take advantage of this PSF because you have sampled it densely enough. But in some cases, maybe your sampling density is much lower. Maybe it's something like this. And then in this case, if this is one image line, and this is the neighboring image line, then it doesn't help you that much that your PSF is very small. Your resolution will now be something like this. This will be your resolution, and it's limited by the pixel size or the distance between your beams. So you can try to, once you have beamform now, you can try to upsample by interpolating neighboring beams, but you won't gain anything from your small PSF Now your PSF could be this large, and you wouldn't. You still would see approximately the same thing. So image resolution can be worse than your extent of your PSF, but the extent of the PSF is a bottleneck for resolution, and the line density is another bottleneck. Okay, so as I said, some of you have been in contact with people from the ultrasound group regarding masters and project assignments, and for those of you who are relevant for those, we will probably try to contact you now, like either today or early next week, to clarify whether or not you should do an assignment on ultrasound. So some of you may continue within this field, regardless of if you're doing that or not. Then the course contains a lot of fundamental signal processing that is useful both in general acoustics and in signal processing in general. Understanding figures and spectrums. These kinds of questions, I think I'll just not answer those. So I guess the best way to prepare for the exam is to go through the checklist and exercises, and those should define the curriculum. So and also give you an impression of what to expect on the exam. So the main line is that we to distinguish students, we need to test both language and understanding and ability to do design choices. Okay then, so that's it for this year. So whatever you're doing in the future, best of luck, and see some of you if you continue working within this field, or if you take more ultrasound courses. So maybe I'll show up. Thanks for that. See you then. Bye-bye.